I suspect what was actually said was, Jim, what are you having? Oh, pint of lager, please, Francis. Okay, that'll be a pint of lager and a Guinness, please, and 2 packets of pork scratchings. Or something like that. Anyway, far be it for me to ruin the romantic dreams of the credulous. But I have little hesitation in saying that in February 1953, when James Watson and Francis Crick, with inspiration from X-ray images made by Rosalind Franklin, proposed a structure of DNA, a monumental step forward was made in deducing the centerpiece of life. This molecule is the code that contains the instruction manual from which living things on Earth are made, the cipher of the cell. When the secrets of this molecule were unraveled, it was not surprising that those who surveyed its features would, for many years to come, consider DNA a freak, a chance product of evolution, a molecule whose structure was special. Its architecture seemed so unlikely that if anyone was asked whether such a molecule could evolve on another planet, they would probably have answered that it wasn't impossible, but that an event of such low probability would be astounding. In an early paper on the evolution of the genetic code, Crick himself described it as a frozen accident that occurred at the birth of life, got fixed in the very bedrock of living things, and once there, could not be displaced without a catastrophic effect on the cell, probably causing its death. Once such a crucial code and its entourage of structures to read it were in place, the smallest error or alteration would be fatal. This view is compelling, but seems increasingly unlikely. At this next level down in the hierarchy of life, from cells to the molecules that encode and fabricate their form, new light has been shed on evolution's choices. Here, too, we have begun to see the indelible mark of physical principles operating through the chemistry of living things, channeling and cajoling the code of life into an edifice that seems to have very much more to it than the mere quirks of chance. Take this molecule, a double helix. Unwind it flat and place it down on the table in front of you, magnified. On your left and right are the 2 backbones running down the table toward you. Made of repeating units of phosphate and ribose, a simple sugar, these 2 chemical struts of the DNA ladder hold the whole molecule together. Between them, running down through the middle, are the guts of the machine, the rungs of the ladder. Sequentially attached to the backbone on the left and right is the 4-letter alphabet of the genetic code, made up of adenine, A, thymine, T, cytosine, C, and guanine, G. Strung along, one by one, in endlessly varied combinations, those nucleobases spell out the information that the cell will read to grow, repair, and build copies of itself. These 4 little molecules are peculiar, for they bind to other members of the group in a very specific way. An A can only bind with a T, and the C only with a G, and vice versa, to form a pair. As the letters of the code have this very fussy binding preference, if there is an A on the left, then there will be a complementary T on the right, and so on. Traversing through the center, attached to the 2 backbones of DNA on either side, are these base pairs, A's and T's linked together, spiraling down the center of the double helix, intermixed with pairs of C's and G's. Right here, we have the first suggestion of something strange. Few molecules in nature have this tendency for a very particular ability to lock onto another to form such a small and tight little family of structures. A freak accident, it seems. This apparently odd property was not lost on Watson and Crick, who observed in their paper describing the assembly of DNA